So in today's session, we will be looking at HBase. So the assumption here is like you already have a slight idea about HBase, but still I will try to go with the very basic and try to walk you through architecture. And as we go in our further sessions, we will start going deeper into HBase. So the intent of this session is to give you an idea about how we run HBase in a production, right? So what are the challenges we face? Because setting up as HBase as a test environment, there will be a lot of things which we will not bother about. So I will be touching upon those kind of things. Okay, so let me just mute everyone once again. Okay, so let's get started. So let me start with a quick introduction about myself. So my real name is Gurmukh, but I am popularly known by the handle Aman Singh because that's the name which is easy to say by a lot of people. So I'm using my nickname, which is my handle, and you will find a lot of videos, a lot of content, and a lot of content development I have done for a lot of the training, online training providers by that name. I am certified on both Cloudera and Mapper, and also I am an Red Hat certified architect. I'm also an author on two of the books. One is Monitoring Hadoop, which was released 2 years back, and other one which released this year is Hadoop 2 Administration Cookbook. And I've been in this industry for more than 14 years, mainly into systems engineering and design. And in the last four plus years, I've been into big data. So I started my journey with Yahoo, got introduced to Hadoop during my role with Yahoo, and ever since then, I've been kind of inclined and interested in big data. And I've been working only on big data. And I am a founder of a company which is called NetZilon Technologies, which is mainly into consultancy and training. And I maintain a GitHub for all the participants. So this GitHub is a public GitHub. So a lot of people use it for their Hadoop as a Hadoop knowledge base. So I this is the link I can share you. So if you go into this GitHub, you will find a lot of information related to Hadoop, right? So how we run Hadoop in production. For example, how you will be setting up a DNS for your Hadoop cluster, how you set up availability, high availability, both using JQM, Quorum, as well as shared NFS, HBase, lot of nodes, and lot of tuning things, lot of things you can see up here, right? So I will just ping it in the window so that everybody can note it. But anyway, all these things will be in the uh, presentation, so you can refer them anytime, and I will also be recording it side by side. And in addition to that, for today's session, I will be using my mini cluster, which will be a 4 node cluster. When I say 4 node cluster, it means the, okay, I think somebody went on speaker, so I've just muted it. Okay, so when I say 4 nodes, there will be 4 data nodes and 1 name node, although you can see another running one, but I'm using presently only 1 name node as an active name node. Another I will be using as an HA just for HBase, not for name node. and I have one node which is running as a job tracker or resource manager, you can say, in Hadoop too, and another one will be an edge node. Edge node is a client node, and we will be using this for our this session to give you a demo. So let's start. So as I said, the objective of today's session is to walk you through architecture, a little bit of working of HBase and operations, because it's very detailed process. Like, we cannot go into detail each detail of HBase working, but I will try to walk you through some of the common pain points we have to look through when we are planning to run a HBase cluster in production, and what things we look to optimize. I will also walk you through read and write path. So why it is important is you should be aware of when you are optimizing, let's say, HBase for read, you should be knowing what all components or what all parts it hits during a read operation. So first of all, HBase, right? HBase is a distributed, scalable, NoSQL database. So the common term we can say it's a non-relational database which is distributed and scalable. So why it's distributed? Because natively it is designed to run on Hadoop, and Hadoop has a distributed file system which is HDFS, which is by default a distributed file system, right? So when we run HBase on top of it, it acts as a distributed system on that. It is designed for random read write access, right? This is the amazing thing about HBase. So all those guys who are already familiar with Hadoop and HDFS works very well with sequential read write, right? But on top of that, HBase has been built for random read write access, right? So this is a common question which comes up, that how it is able to do a random read write access, although the file system which it is based on is a more mostly designed for a sequential access. So I will try to explain you this today after going through the design. We will look at why it's able to do that. It can scale to petabytes of store with thousands of nodes, and with each node having many regions. And in a total cluster, I can have multiple regions. So we'll look into what do we mean by when we say a region. It supports sharding or partitioning by default. So all those guys who are familiar with let's say a databases, let's say a MySQL database, you know that as the table grows, we have to partition the table. It's called sharding. We will take a table, let's say a table had 1 million rows, and as the table grows, it will be very difficult to keep that table on one single node. So what we will do is we will partition that table, maybe let's say 250,000 rows, and divided it into four parts and spread it across four nodes. But we have to do that things manually, and there are a lot of care has to be taken how we shard, and we have to take care of a lot of properties in that. But the beauty about HBase or all these distributed databases is, by default, they are designed for sharding and partitioning. So the moment a table grows beyond a certain size, it will automatically be split across multiple nodes, so as to maintain quite a reasonable size of a table on one particular node, and also to balance the distribution across the nodes we have in a cluster. And another thing what HBase does beautifully is it balances the data across nodes in the cluster. So I'm not talking about balancing from an HDFS perspective, right? That is entirely different thing, right? Where the name node takes care of balancing the distribution of HDFS blocks across the cluster. This is HBase, right? Which is a distribution based on region. So let's look into this part. So let's look at architecture. So this is a very simplified diagram of an HBase architecture. So HBase, similar to how Hadoop is also a master slave model in which we have a master and we have slaves, right? So it's a master slave model, or in simple terms we called it as it's a server client architecture. So HBase is also an server client architecture in which we have a master and we have clients which talk to master, and they periodically update the master about their status. So we have an HBase master here, and the clients, they are called as region servers. So each of the region server will have certain roles to play, which we will see, and this file system will be laid on top of HDFS. It can be any other file, it can be Lucene, it can be S3, right? It can be any, but by default it will be HDFS. So let me give you an idea here what actually happens in this architecture. So by default we will have a master, right? So this will be my, let's say, a master. This is my HBase master, and then I can have multiple nodes, maybe one or multiple nodes. Each of these nodes are actually data nodes, right? From a Hadoop name node perspective, each of them are data nodes. But on data nodes we will be co-locating the clients for HBase, which will be called region servers, right? Region servers. So what is a region server? Actually it will be a daemon or a service running on a node, and it will be co-located with data node for data locality, and it will be sending, these nodes will be sending constant heartbeat to the HBase master, right? So all will be a region server I will be representing as RS. So each of these nodes will have a region server, which is a daemon, which will be constantly sending an update to the master saying we are alive, and these all set of tables or regions we have, right? So this is a very simple overview, but as we go ahead I will show you it is not the actually the master which is taking care of it. There is another component in between which sits, which we called it as Zookeeper. In an HBase cluster, let's say if I'm not doing any of the DML operations. What are DML operations? Create table, alter table, right? Region splits, those kind of things. I do not need master, right? In my cluster I can even shut down my HBase master. My cluster will still do read write, but it will not do DML operations, right? So we will look into that. So let me go back to the slides, and as we go there I will talk about that. So I will explain you this in detail. What does this mean? So this is what I was talking about. So each of the data node here will be a region server, will be running a region server daemon on it, right? It will be running a region server daemon on it, and all these region server daemons, they will be sending a heartbeat to the Zookeeper. So they are not sending heartbeat directly to the master. So there will be an intermediator sitting, which will be a Zookeeper, and Zookeeper will be updating the master about the status of the servers we have in the cluster. So Zookeeper is kind of a distributed coordination service. So you can think it as let's say you go to a zoo. So Zookeeper is a someone who is taking care of or coordinating the animals in a zoo. So Zookeeper is a service which is coordinating all the players in a cluster. Zookeeper works on the basis of a consensus protocol or consensus algorithm. So what it does is it keeps track of what nodes we have and what kind of data they contain, right? So I will come to that when when we talk in detail, when I talk about what kind of data they contain. But for the simplicity, for the time being, so region servers will be updating their status to the Zookeeper. They will be checking inside a Zookeeper, and Zookeeper is the one which will be updating the master. So let me show you the architecture a little bit here, how it is actually working. Let's go to a node, right? So this is my client, but let's say I go to my HBase master. If I do a JPS there, you will see a name node is running and HBase master daemon is running. If I connect to any other node, let's say I connect to my data node and I do JPS, over there you will see my name node, node manager running, my data node running, and my region server running, right? So how I have simply started, I've simply started my HBase like this. Let me, if I stop it, right? If I'm not going through, as I said, this is not a very introductory section where we are not talking about how to set up HBase, but still, if you are interested how to set up HBase, I've given all this in my GitHub. If you go to this HBase folder, it talks about what files we have to put, what commands we execute, what to do about that, right? But as I said, this session is not about setting up HBase. This is little bit next step to HBase. So I say start HBase. So if you look here, it will do when I stop the HBase master, it will stop all the services in my cluster. But once the HBase master is started, the regions have come up. So what these regions will do is, actually these regions will update or check in to Zookeeper. Even the master and all the data nodes, they will check into Zookeeper. So where is my Zookeeper running? If I do opt cluster, right, depending upon the path, wherever you might have installed it. So if I do this jk client dot sh hyphen server, and I'm giving my host name, because Zookeeper, one of the Zookeeper node is running here. So I'm running 3 Zookeeper nodes here, right? So this is my Zookeeper. So if I do ls here, you will see it has z nodes, right? So z node is a concept of a zone for a Zookeeper, where it will be keeping a zones for each of the service it manages. So when I started HBase service, what it does, each of the node will go and register itself with the Zookeeper. So if you go here and let's say look under master, these all folders will be containing states of what is going on, right? For example, let's say if I say rs, right, it is telling me what all nodes I have. Backup master, what tables I have. Whenever I create a table, it will go into this entry. It will be first updated inside the Zookeeper, and from Zookeeper it will be distributed. Master will know there is some table called, let's say, employee. So by default, there will be two tables created by HBase, which will be, one will be HBase meta and other will be HBase namespace. So these are called catalog tables. By default, catalog tables in HBase. Currently, our cluster does not have any table. So as the cluster goes, right, as the cluster work progresses throughout its life, we will see a lot of changes happening in these folders. Like let's say whenever we write something, a split happens on a wall. Wall is a write ahead log as we have in MySQL, or a backup master, or a table log, right? All those things will be logged in here. So I will quit here, and my HBase master is running. So I can access my HBase master on 16010 port. right? So if I go here and in my this one and I say IP of my node and 160.160.1.0, what is telling me my master is this and then one. I have 4 nodes and there is one backup master also, but currently I don't have any tables, right? If I go to tables, I do not have any user tables, right? Obviously it will have the catalog table, which is .meta and the namespace table. So we will look into that, what those tables are, and it will be telling me what is the Zookeeper path where it is keeping, and what is my HBase root directory where it will be storing all my data. So if I go to my HBase cluster or Hadoop cluster, I do ls hyphen fs hyphen ls. So there will be a directory, it will automatically create. I don't need to create this. Whenever I start my HBase service, it will create that. So this is the directory where it will be storing its data, wall files, right? And a lot of other things. So I will come into that. What is wall file, what is H file and all. But this is a walkthrough of the cluster. So each of the node you saw is running a data node daemon. It's running a region server daemon, and they're checking into a Zookeeper, not directly to a master. Zookeeper is updating the master. So I can shut down the master once the cluster is up and all the region servers have been up. So I can shut down the master. So it will still keep on working. But it does not make sense to keep it down because I might need to do a lot of things. Let's say create table, other DML operations. So in production, we will not be keeping it down for very long. But yes, just to explain the understanding, for the sake of understanding, we do not need to keep it up. So before going into HBase details and architecture and all, let's understand a table in HBase, right? So a table will be similar to any other table, how you create in MySQL and all, but how it differs is it has a concept of column families. So it is a way of grouping certain rows and columns into a grouping, right? So for example, this is a very simple table, and in this table I may have 2 column families, let's say personal data and professional data. So these can be grouped per column family, right? I can have a flat table having only one column family, everything inside one column family, or I can have 2 separate column families. So what is a column family? It's actually a group of cells in a table which will be stored together. So when I say a column family, let's say a personal data, so there will be a separate storage for that as compared to us, what, where does that professional data goes, right? So I'm explaining this in a very layman term, but there are a lot of details like H file, where it goes, how the mem store flush and all. But for the time being, each of the column family has a separate storage. So by default, when we create a table will be a group of some rows. Let's say I create a table which has only 10 rows. So this table will be stored on one particular server in my cluster. So let me go to the whiteboard and explain you. Let's say I have a table, and this table has, let's say when I started, it has only 10 rows, right? So let's say these are 10 rows. So this table 1 2 till 10 rows, row ID 10 rows, and it has some entries inside that. And let me just change the color. Let's say this one is one column family, CF1. This one is another column family, right? I will show you how we define column family from a command line. So the purpose of column family in a table definition is how they will be stored on a disk. So when I'm saying a column family, this section will be stored in one part, one file. This second portion, this will be stored in a separate file. right? So as I said, when I start my table, this table has 10 rows. So this table will go to any region in my cluster, any region server. So let's say I have 4 nodes in my cluster, 4 data nodes. Let's say data node 1, data node 2, data node 3, data node 4. So this table, let's say it goes to data node 1. It is a small table, only 10 rows, so it can sit on that particular data node. So this data node is running a region server, which we called as RS, which is a region server. So region server can contain multiple regions. Now let's understand what is a region, right? So we saw region server is something, it's a daemon, physical daemon. You can see on a node, you can do a JPS, and you can see there will be a process running on a node, which is a server daemon. But what is a region? So region is actually a part of a table or a complete table. So let's say I started with my this table only has 10 rows. So this table has just one region. Presently it has only one region, but as the table grows, it might, let's say it might split into multiple parts. So each part is called a region. So when we start with HBase or create a table and the table is small, it will be just having one region on any one particular region server. As the table grows, it will be split into multiple regions, and that regions will be distributed across the nodes in the cluster. So let's say if this table grows to, let's say, 1 million rows, I'm giving an example, 1 million rows. So this will be split into multiple regions. Let's say this got split into 20 regions. So now I have 4 nodes. So it will split 5 regions per node, right? So let's say region 1 went here, region 2 went here, region 3 went here of this table, region 4 went here, then region 5 again went here, like this, right? So it 5 regions went per region server. It will be distributed. But I will explain you with an example what actually it is doing. So as I said, each table is composed of column families, and each of the column family will have its own store, right? So what is a store? Let's go back into the drawing board, right? So let's say I have a table, right? Very simple table, and this table has some rows, and let's say this table had 3 columns, right? But this is one column family, this is another column family, right? So one column family can have multiple columns as well. I was just checking, I was hearing some noise. Okay, so I can have multiple columns per column family. Means let's say column family 1 may have thousands of columns, but for the sake of simplicity, we are just keeping one column as a column family. So what does it mean? This column family, this particular column family will be having its own store. So what is a store? Store is a combination of mem store and an H file. Mem store is a buffer in the memory, which is by default 128 MB. And this mem store will be flushed to disk, and it will create a file which we called it as an H file. And similarly for this second column family, it will again have a store which is a combination of your mem store and your H file, uh, right? An H file. So each will be kept separately. So what is an H file? H file is a special file which will be written to the disk on that particular data node where the region server is running. Means the storage will be anyway on HDFS, but this is a special file in which will be containing information per column family of a table, and it will be sorted in a sorted order. So before the data is flushed from memstore to H file, it will be sorted. And as the time goes, let's say I may have multiple H files, right? As because my memstore flush is only 128 MB, so it has to flush to empty itself. So it will keep on creating H files, and after some time, these smaller H files will be combined into one larger H file. Again, all three H files will be looked together, again resorted in a sorted way, created one file. So there are different kind of processes which does this merging, which are called minor and major compaction, right? So lot of details, but we will not go into that. I'm just giving a very brief introduction. So what is happening when a record is written? What is the path it follows, right? So let's say in MySQL, I'm making any change to my data. So what will happen is, first it will not immediately go and make a change and go into your direct uh, store file. It will always go to a log. In the case of MySQL, we called it as a bin log. It will be a write ahead log, so that in case some crash happens, I can replay that log and recover my data. So similarly in HBase also, we have a wall. Wall will be sitting on HDFS, right? So as I showed you in this directory path, there will be a walls directory. In this directory, there will be a wall written. So let's say whenever I write something in my HBase table, it will be first written to this wall, right? Remember, it is not written to memstore first, it is written first to the wall. Then this wall is emptied into memstore. Memstore is then flushed into my H file, right? So this is a sequence it follows. Right, so this is what I have explained here. So as the table grows, it splits into regions, and regions can be across multiple nodes. So this is what we discussed. As I said, as the table grows, it will be split into multiple parts, which we called it as regions, and those regions will be across multiple nodes. So whenever any store of a region is flushed, all stores of that region are flushed, right? So very important, right? Again, from a optimization perspective. So what it means is, let's say in a table, I've designed a table in which I have a column family which is very heavy. Means let's say this column family has 20 rows. This column first, let's say first column family has 20 rows, and which are heavily written. My, like, let's say my data which is coming in as a feed, let's say my data is a sensor data, right? I'm taking some real-time sensor data, and the fields which are coming in, they are constantly coming for this column family, and this column family 2 which is here, hardly a few records come once in a while. So what will happen is, this one store will be getting full at a much frequent rate, and memstore needs to be flushed much more frequently as compared to the other one. But as they are part of the same table, all the stores of a region will be flushed at the same time. As I said, how the region is split happens, region split is happening like this, horizontally. So in one region there will be all the column families, let's say column family 1, column family 2. So if a store flush of a column family 1 store happens, automatically all the stores, other stores will also be flushed. So it means column family 2 will also be flushed, even it might have even a one record. So in the first case, let's say my mem store is 128 MB, and it went to 121 MB of space, and it will be flushed to disk. this might be having just 1 MB of data, but it will still be flushed. So it will create H file, a very small H file. So now, because of my table design, I will be generating too many small H files, which will again impact my one, the name node pressure, too many H file small files. Second, it will be going into very frequent compactions, minor compactions, right? Because there's an algorithm in HBase which will be taking care, which kicks in to compact a group of files into one larger file. So if I have too many small files, that will be kicking in too quickly to do minor compaction, right? So we are not even touching major compaction, which is again a very different topic, but minor compaction will kick in too frequently. So we have to take care of while we are designing this table. So having too many column families per table and not using them evenly could be a bad design. So this is what I was explaining you. Okay, question from Kaushal is, any chances of failing minor compaction? Yes, yes, there are chances, right? So I will discuss what happens here, right? So as I said, like HBase is so vast, like we can keep on going, but I will try to touch upon the questions which come. So this is what I was explaining you. Per region, there will be a mem store and H file, but there will be only one common wall file per region server, right? So let's say I have one region server here. There will be only one wall mechanism per region server, but there will be multiple regions on that and multiple stores per region, right? So wall has to be played for all the regions, common wall. So when I say there will be common wall or single wall, it does not mean that there will be one file. By default, there can be maximum 32 wall files, right? So as the question came from Kaushal, that can minor compaction fail? So what happens is, first thing what it does, let me go to the board, whiteboard. Let's open one more page. So the process, the sequence of write is, first it goes to wall. Wall is flushed to memstore. Memstore is flushed to H file, right? So there can be blocking at multiple levels. By default, how many H files I can have before a compaction is must? By default, it is 10, right? Before a minor compaction should kick in. So let's say I'm pushing too much of data very frequently into HBase. It is going into wall. So by default, the block size of wall is equivalent to an HDFS block size. So what does it mean? Let's say my HDFS block size is 128 MB. So what it will mean is 128 MB, 128 MB, and I can have max wall of 32 wall files. So 2 GB of data at the max can sit in my wall file. After that, it will block my writes till it is flushed to memstore. Memstore is 128 MB by default, right? It will block till there's like you cannot go beyond that till it is flushed to H file. So it can only allow 10 H files, right? So see the loop, right? So in production, when you go and look for all these things, so many things you have to look at. What will be your HDFS block size? Right? Let's say you're given 128 MB. So I'm creating by default 32 wall files. So my writes can maximum be up to 2 GB, which can be stored in wall. After that, my write will block till it is going through this cycle, right? So anyway, this will be a very rare case. Let's say I have a bad disk where it is taking too much time to write to wall and all, but wall is getting flushed to memstore, memstore is getting flushed to H file. So the algorithm for minor compaction is, first of all, is I cannot have more than 10 H files. It will block if I'm creating too many H files till the minor compaction comes in and combines all files into one bigger file. But minor compaction does not always kick in, right? So there is a algorithm which minor compaction looks at. Like it looks at whether it is beneficial actually to combine smaller files into a bigger file for a performance perspective. So it looks at a lot of parameters. How many minimum files it can combine, the maximum number of files it can combine, the minimum size of file it can combine, right? All those things should be true. All the conditions should match, then only it is eligible for minor compaction, right? Minor compaction can fail for multiple reasons. I may be low on disk, I may be low on file descriptors, right? Common problem in HBase, I'm creating too many files, I ran out of Linux file descriptors, right? So my minor compactions will fail. Okay, so this is what it is doing. So this is what I was explaining you. We have a table. So this table will be split horizontally into multiple regions as the table grows, and where that region of a table goes will be kept in a special table in HBase, which we called it as HBase meta table, right? HBase colon meta table. So that meta table will be keeping a record that table A has region 1 and this region 1 is on region server 7, right? Or let's say a region 2 is on server 4, right? It will be keeping a map. So what happens? So when we start the HBase cluster, the meta tables, the catalog tables are with the HBase master. But once the initialization happens, the cluster comes up, that meta table is passed to one of the region servers in my cluster. I can pin that to master, right? I can say that my region, this HBase colon meta table should always be on master. I can say that, but by default the behavior is once the cluster comes up, that H meta table will be moved from master. Moved means it will be actually copied from the HBase master to a region server, any of the region server, and information about that will be updated in the Zookeeper. So whenever a client comes to read or write any record from a table, it will not contact HBase master. It will contact the Zookeeper. It will ask Zookeeper, can you tell me where is my, I think I might have given it somewhere. Okay, yeah. So this is the meta table, right? So it will go to the Zookeeper and ask, where is the meta table? It will tell, okay, your meta table is on region server 4, go. So it goes to region server 4 and it says, I am looking for this row key. Let's say it says I'm looking for row key 4. So meta table will be keeping a map that this particular row key falls in which particular region of, right? So it will be saying I am looking for row key 4 of table A. So it will be having a map saying, okay, so this particular thing what you are looking for is is in this region, and this region is on region server A. So then it will quickly jump to that region server. Once it goes to that region server, then it will not read the entire file, right? So that's let me just go to the whiteboard to explain you this little bit. So the question which came up was how HBase is able to do random read write although it is sitting on HBase, which is a sequential file system. So what it is actually doing is, let's say once from the meta table it came to know, let's say a client comes and says I want to know about row 4 of table A, let's say example, it will go and ask meta table, right? How it will know about the meta table? From Zookeeper. Zookeeper will say the meta table is on this particular node, so it will go to that particular node, ask for a meta table, and in that meta table it will say I'm looking for row 4 of table 1. So this meta table will say, okay, the row 4 which you are looking for table A is part of, let's say, region 1, and it is on region server 4. So it will jump directly to that 4 region server 4, and it will jump into that region server 1, region 1, right? So in that region 1, what it will do, it will not look for row 4 by scanning all entries. It will do the H file which we have. It's a very special file. So H file will have has an index. It will have an index. So this index will be mapped into memory on that region server in the block cache. So it will just go and look into the index, that directory structure. We call this as a Bloom filter in HBase. It will have a Bloom filter sitting in the memory of the region server. It will search in that index. It will say, I'm looking for row 4. So that index will say, okay, row 4 is in this part of the H file. It will directly jump into that H file, means it will seek directly to that location in the H file and read that. So that's why I'm able to do random read write. It will just seek through. It doesn't go through the sequential, all those kind of logic to fetch the block. So let's go back to the slides. Right, so this is what I was explaining. So HBase operation. So as I said, it's a client server architecture. HBase is the master and slaves are the region servers. So clients will talk directly to the region server unless it is a DML operation, like create table, region as a reassign, those kind of things, delete table, all those. You don't need a master. During boot up, the catalog tables are with the master and they are copied to a region server. And this information is kept in the Zookeeper. As I said, this will be kept in the Zookeeper. Zookeeper is contacted for all operations like finding meta table, region server, or a table. Even when we create a table, that table will be updated in the Zookeeper that I have a table, and master will be notified that particular table has been created. This table has this many regions and all those information. So all tables and transition states will be marked in Zookeeper. The location I showed you, each folder you can see whenever you create a table, transition, everything will be marked there. So meta table will have a start key, as I said, a region ID, a region server, and a region ID. So using meta table, you can jump to any part of the region. And once a meta table has been queried by one particular client, it will be cached so that it doesn't have to again go through Zookeeper and find where the meta table is. Right? It will be cached. So this we have walked through. So HBase write path. So as I said, let's say when you are writing any record to HBase, first thing it will go to wall log, right? And it will send a acknowledgement to the region server saying, oh, okay, I'm done to the wall. Once it's done to the wall, it will write to the mem store. And once it return to the mem store, it will acknowledge the client that your write is done. Right? So see the path, it is going to wall. Wall is getting flushed to mem store, and then only it is acknowledging the client that write is done. So you might see sometimes you are writing a record and it's just hanging over there. It's taking very long time because it is going through this cycle. Maybe your disk is slow, disk is bad, or your memory is taking time to get flushed to the disk, right? And then at a later stage, once the acknowledgement is given to the client, it is flushed to the disk at the back end, depending upon whenever your mem store gets full. So in the read path, what it does, it reads from the H file where it is storing data. It reads the block cache also. Block cache is a location it's a buffer in the memory where it will be caching the data. Whatever you read, it will be caching that, so that next time you don't have to go to disk. So when you are reading, what it will do, it will go to H file, it will go to block cache, and it will also look in memstore for any latest updates. So it will be doing a read amplification, means it will going to 3 locations to see, do I have the latest record, and give you an answer or the latest data. Now we have just walked through very basic overview, but now let's look at what could go wrong in what we have discussed. What about the size of memstore? As I said, right, so by default the memstore is only 128 MB. So I can increase it to reduce my flush cycle. Let's say I make it to 256 MB, but obviously my node should have that much memory. So if I have a table with many column families, so I will have that many mem stores per table on a region server. So let's say if I'm bumping one mem store, so all will be increased. So let's say I have 10 column families. So if I'm increasing mem store, so mem store will be increased by a factor of 10 because I have 10 column families in that table. So smaller the mem store, more frequent will be flushed, as I explained. So more will be the smaller number of H files. So more the number of H files, as I said, by default it allows only 10 H files to be created. Otherwise, it will try to block your writes. So more frequent will be your minor compaction. So you have to do a minor compaction. So you will see your write performance going down. And again, similarly about wall, as I explained, wall will be equivalent to, by default, the wall size will be equivalent to your HDFS block size. And I can have 32 wall files. And I can do a lot of things in wall files also. For example, I can do multi-part wall file, means multiple threads writing a wall file, right? But by default, there will be only single thread who will be writing a wall file. So a lot of things we have to look there also, depending upon all these will you have to look into logs. Logs will be saying what is happening to the server. Now, as I said, when we create a table for the first time, it will be just sitting in one region, on one particular region server. But as it grows, it will be split and spread across. So splitting will also cause problem. Why it will cause problem? Because data has to be moved across. So let me explain you this on the board. So let's say I have one table which is sitting on node 1. There is one table sitting here, and this table got split into 2 parts. And this table is moved to some other server. Let's say server 2, data node 2. So when the region is moved, let's say this was on data node 1. The HDFS blocks of this table are on data node 1. Although this part of the region has been moved to data node 2, the blocks are not moved, right? The blocks will still be on data node 1, right? So HBase is moving the regions across to balance the number of regions per region server, but HDFS blocks are still there. So whenever I have to read some data, I have to make a cross network call for that, although the regions are moved to a different region. So these blocks will not be moved to this server localized till major compaction kicks in, right? So major compaction has two roles, right? Minor compaction was what we discussed. It is combining smaller H files into one. It is kicking in very often. Major compaction kicks in by default once in a 7 days. Right, so in production we will always disable major compaction. We will be doing major compaction manually in off-peak hours. So because major compaction is a very extensive process, it takes a lot of memory. It tries to take all the files and create one file, and also it will be doing delete operation. Let's say I've deleted a record, some table or some entry in a table. It will not be deleted immediately. A marker is put and it will be deleted only when major compaction happens. Another thing what major compaction does is it does localization of your data. So imagine that's why we are keeping major compaction always in the off peak hours. One, it is merging files. Second, it is also doing locality of data. Although the region was moved to DN2, but blocks were still on DN1. So when major compaction is fired, these blocks will be localized on DN2, right? So it will create network traffic. So all these things need to be taken care of. Now another important thing which we have to take care of is, now let's say my cluster is operating, I'm writing some data, and region split happens, right? So region is moved from one region to another region. Let's say by default this was region 1, very big region, but now after as it grow, a split happened, and this region become region 1 and region 2 moved here. My client was reading data from here. Let's say here was row 101, right? Let's say 100 was till this point. From 101, this got split and moved somewhere else. My client was reading here, but now this region moved. So my client will get an exception saying region not found. Again, it will retry. Then Zookeeper will redirect him to this server saying, oh, region has moved, but you will get an exception. So in a busy cluster, when you are doing too many writes and clients are reading and all, if there are frequent movements of region, then I will be seeing lot of exceptions, right? And movement of region is also an extensive process. So we can all control this. When a region moves, should region moves, how we can do that? I can pre-split my table, right? Rather than saying start with one region of a table, I can start with empty table. I can say empty table split before I load my data into 20 regions. Let's say I'm aware of my data, that with data which I will be loading into my table will be, let's say, 100 GB. So why wait for my data to be loaded and split as I load? Why not split in advance each region of 10 GB? Create 10 regions, each region of 10 GB, so that there's no split happening. There's no movement of regions across. Second important thing we have to keep in mind is, by default, after HBase 0.94, the HBase split policy is different, right? What is the split policy? So HBase has a region split policy. So by default, after 0.94, the split policy is upper to bound split policy, right? I may not be exactly saying the name correctly, but let me show you what is the by default HBase region split policy, right? So it is policy. So it is upper to region split policy. Yeah. So this is the policy, increasing to upper bound region split policy by default from 94. Yeah, that I was correct. So this is the by default policy. So what this policy means? So let me go to the board. So I have a mem store. Mem store, which is of 128 MB by default. It flushes at 95% of its usage. So it flushes at 121 MB. It creates an H file. So in this new policy, upper to bound split policy, whenever the first split happens, it will split the region. Means the first split will happen at 128 MB. Second split will happen at 256 MB. Third split will happen at 512 MB. Fourth will happen at 1 GB. So it keeps on like incrementing to upper bound and keep on splitting the region. So what is the disadvantage of this default policy? When I'm inserting my data, you will see many splits happening in the beginning. You will be seeing timeouts happening on the region servers because regions are moving across and your clients are not able to find regions because they have been moved across, and also split being happening, and split also creates load on your region servers. So by default, this default policy, if I'm having an HBase cluster which is write extensive and I'm trying to optimize for it for write, so I have to make sure that this split does not happen very quickly. By default, it is splitting at these boundaries, and this split happens till 12 GB, till 10 GB, till it goes to 10 GB, then it stabilizes, then it starts splitting at 10 GB. So what we do is we get rid of this and we go to the original policy which we used to have before 94, that was constant size region split policy. In that we will say a size that do not split before this particular size. I will say, let's say 10 GB. So I will let my region grow to 10 GB, then only split. So what I'm avoiding that split overhead on my nodes, the timeouts, the movement, all right. So now we have looked at two parts. One is this split policy to avoid breaking of splits, and also we have looked into the other aspect where we have looked at how regions will be moved across by creating a pre-table, pre-split table. Another thing, important thing we have to look here is there is a balancer which is running in HBase, which is trying to balance the number of regions. Right, this is different from HDFS. HDFS keeps a balance on the number of HDFS blocks across the nodes. This is balancing your regions. So let's say I have a server, right, as I was giving you example here. So I'm writing some data and this data is written to, let's say, my region server data node 1. My table is initially on data node 1 and my table is growing, and now it is splitting, creating many regions. So let's say on this it created 10 regions, and I have another regions servers in my node which are empty. So balancer will kick in and it will say, oh, these three servers are empty and this region server has 10 regions. So what it will do, it will try to move to balance it. Right. So by default, it kicks in every 5 minutes. So I can increase this time also. Right. I do not want regions to move when I'm doing a bulk upload in my cluster. Right. Or whenever my peak workload time is in my HBase cluster. Let's say early morning, I get a very intensive flow of real-time stream from sensors, let's say between 9 a.m. to 12 a.m. So at that time I should make sure these movements are not happening, so I can bump up the balancer timer so that region balancing does not happen, kick in that time. I'm not saying you should disable, right? Balancer is a good thing because it is trying to balance the number of regions across your cluster, but still I am trying to control that particular movement when I'm doing bulk load into my cluster. So let's go back here to the slides. Too many splits, region balancer, right? Data locality, as I explained, although the regions move, data will not be local till major compaction kicks in. Right? When you should be making major compaction, always in the off peak hours. It's a stop word event because it does a lot of things, as I explained. HBase table design, right? It is very important. For example, if I'm designing a simple table which is a time series based, right, rows, then I will have hot spotting. Okay, I have a question from Suresh. Suresh is asking what will happen if one of the region servers is down. Okay, see, let's go back to the slide here. So question from Suresh is, let's say I have this region server and this region server had regions. let's say region 1 and region 4. And this server, due to some any error, let's say hardware error or whatever, this region server went down. So these regions which are on this nodes, they will not be accessible. So how HBase is taking care of these kind of scenarios? It is taking leverage the beauty of HDFS at the underlying layer, right? So HDFS by default has a replication of 3. So that blocks which were here, which was part of this region, which was on this region server, will be somewhere else according to your rack awareness locality of data. So when this region server goes off, so Zookeeper will know that this region server is not sending a heartbeat. It will ask region server, tell that HBase master that this region server, I'm not hearing anything from this. This has gone down. So it will look, okay, what all regions were on this one. So it will bring those regions up on another nodes in the cluster. But yes, it will take some time for those regions to be up. How much time it will take? It will depend upon multiple factors. For example, what is the Zookeeper timeout for it, right? What is the timeout I have given for a heartbeat? What is the time it takes for it to update the regions, and how quickly it can bring up those regions on those nodes, right? But yes, at that particular time, let's say a client comes, tries to read it, it will get an exception. Once a client gets an exception, it throws out its cached meta table, right? As I said, once a client comes to know about a particular meta table, it caches it and it keeps on referring it. But once it gets an exception, it drops it and again reloads it, and so that with an updated information about region, and then it starts again going to the right regions, right? But if my replication is 1, that's a bad design, right? In HDFS, if I keeping my replication 1 and one of my node goes, I will have data loss, right? Similar to what we have in HDFS. So as I was talking about salting, so what is the concept of salting, right? So let's say I'm designing my table, and my table is something like this, a very long table. And in this, my table, the first column is, let's say, a row ID. This is a row ID, or let's say a roll number. Example I'm giving. It's incremental, 1, 2, 3, 4, 5, and it keeps on incrementing like this. So what will happen is, it will be creating hotspots. Why hotspots? Because I will be hitting only a particular section of table always on a particular node, right? So let's say another example. Let's say if I give my row ID as date, right? So always this date will be incremental. Let's say we are in the month of August now, and now let's say it is 1st August to let's say 30th August, right? So what will be my need? Obviously I will be querying my recent data. I will be interested in whatever is my data in August. So where is my data of August lying? It will be lying in one particular region, because it's all sequential, right? Because it will be falling in that particular region. So it will go to one region server. So every time I'm querying, it will be wholly hitting one particular region on a one particular region server. So I will start seeing hotspotting. So that's why we say we will be always salting, right? So there are a lot of salting libraries available by Phoenix tool, or I can simply do salting by my simple logic, right? So which will distribute my rows across multiple regions in my cluster. So I will show you example of that, how we do that. I will quickly show that. So let me, okay, good, we have come to the demo. Let me quickly show you on my cluster how we can do that. Let's say HBase shell. Let's go here. So you don't need to note down anything. I have uploaded for this session. I have loaded one folder under my GitHub path. If you go to this location, right? So let me just paste this to everyone, right? So I'm sending it to entire participants. You can keep a note of this. This is a public repo. Anybody can access. You go to this HBase folder, right? So all these are talking about how to set up, but you can go to optimizations, where I've given a lot of things, benchmarking, a lot of things. Let's say I go to a create table statement, right? So the example I give you was employee table. So let's say I can do very simple thing. I can do a, let's say, a create table. So here, let me go back to the slides, right? Right, this table I'm creating a table with two column families, personal data and professional data. So this is what I've done, a table name employee, and it has column family personal data and professional data. So let's go back here and insert some data into it, right? So I'm not talking about splits and all that now. I will talk about a little bit later. So let's talk about creating data, right? So one thing is I can simply add 1 2 records into it, right? Or I can add, as I will give an example here, right? So if I run this bash script, see, it will be creating a very sequential kind of data, and you will start seeing hotspotting. But what I can do instead of that, I can do a random number generation, right? Employee ID, so it will be a random number generation. So as I said, in an H file, it will be sorted. So let's say I might have got some random keys in the range of, let's say, 10,000, 20,000, 40,000. It will be arranging writing to H file. In maybe in the second instance, I may get a random key 1 4 10 20 40. Again, it is sorting, it is going to a separate H file. So it will be keeping it separate, right, for optimization. So this is how I can do a random number generation. So let me just quickly generate a very small file just to load it, right? Let me go to a data node and we say gen.sh. I'm just giving a name. I will just reduce the number of records, right? Let me just, instead of having so many records, let's create only 1,000 records, not more, right? So let's create only 1,000 entries, and I'm doing sh gen data, and I'm saying load something. Sorry, let me, it will be easy if I create on the same node, because otherwise I have to redirect the file ssh and then one.cluster1.com, right? So I'm just doing vi gen. Okay, already I have that. Okay, this is something else. Vi gen 1.sh, right? So let's do sh gen 1.sh, and I'm saying load, cat load. I've created some data. So now I will be loading this data, hbase shell, right? So I'm loading this data, and if you can look into this, I've just created records, employee table, some ID, and the column family entries, and I'm saying load. I'm doing a redirection to that file, and it will be reading that file and executing all those commands. It's just 1,000 records. It will not take much time. Right, so I can do list here. In the meanwhile, the records are loaded. I can do status. Status will tell me information about how many servers I have. 4 servers, 1 active master, 1 backup master. So if I go to my UI, now you will start seeing a table, default table, right? And it is also telling me which table region server it went to, right? 4,000 requests, right? It it did. Locality is currently 0, right? Why locality is 0? Because it's still there's no data loaded to that. As we are loading data, you will see it will change. Okay, right? So I say list, it is showing me table, EMP table, and I can do a scan on this table, right? So it will list me all the columns it has, entries it has, right? So it will be telling me the number of requests and all. So I can go table details, I can look what table it has been created. So by default, like, all this has a lot of value. So as I was telling you, what it will be keeping in the Bloom filter, all those things in memory, whether we are keeping or not, how many versions it's keeping or not, all these things, right? So now let's look at some more information inside this. Let's go to GitHub. Let's say I want to look at meta entry, right? I want to look into the meta table, that how this table looks. So now I'm looking into that meta table. I'm scanning HBase meta and I'm doing a filter on that prefix of employee table to see how my table is arranged. Right? It's a very small table yet, right? So it is telling me that this employee table is on this node, right? Only one region it has, because it is telling only one node. But as I keep on adding records, it will keep on moving it across the multiple nodes. Right now it has only one region. So let me just for example just disable it, EMP, and drop it. I think we are running out of time, but just let me show you one quick thing. There are a lot of things, but this is just a first introductory session. So let me, now I will be creating now a table which will be pre-split, right? I can pre-split this table into multiple regions, right? I can say split this region into, let's say, 100 regions, 20 region, or 40 regions, something like that. But let's say I create this into I just split this region into 20 parts, right? So I'm defining a variable, and splits is equal to 20. Any name you can give. I can give my name Aman is equal to 20, right? What I'm doing is I'm just using that variable to just create tables map, right? So what will be doing is I'm doing something like this. So here I'm giving that 1 to 20 splits. What this map function is doing, I'm giving a specific region names to that. By right, I can, but if I don't give this name, it will be taking some number. But just to identify, it's giving a user, right? I can give any. Let's say I can give EMP here. So EMP, right? So I can now identify in my logs and everywhere that these regions which are, they are of the employee table. So I hit enter here. So it will be creating now 20 pre-split regions of that. So, right. So now let's go here to my cluster and I say tables, EMP. Now see, now this table is at many places. Right. So there are so many things which we can do here. Right, we can do snapshotting and all, but that comes much later. There are a lot of tunings which we have to do. So I hope this session was somewhat useful for you. I will upload the recording of this, and if you have any questions, feel free to reach out to me by email. So it doesn't matter, your question might be related to this session or not. So this is my email ID. You can reach me for help or guidance. Do not think that you have to reach me only if you need training or anything. Nothing like that, right? A lot of people reach out to me for any questions or any guidance they need. So you're most welcome to drop me an email with any questions you have, and I will be more than happy to help you out. And I have a YouTube channel. You can watch that YouTube channel where I keep on uploading videos, which will give you a good insight into what's going on. So let me see if anybody has any questions here. Okay, so I think we have run our session almost by 20-25 minutes more than our scheduled time. So thank you very much for your time, and feel free to reach out to me for any questions you have or any queries you have, and I will be able to assist you on that. Right? Thanks very much. Have a great day, and looking forward to see you in next sessions. And if you are interested in looking for any particular session, let me know also in the meetup or by email, and I will try to arrange that. Thanks. Have a nice day. Bye bye.